Hello everyone, and welcome to the first session as part of the SZ workshop, which is about the practical IEC 61850, the standard for substation automation for engineers and technicians. So this is pre-recording number 1, and the topic for this is substation automation functions to be recorded for you. So basically, the idea is for this course to give you an understanding of the concept and the applications of the standard IEC 61850 in terms of the substation automation practices, as opposed to traditional systems or other substation automation techniques. Obviously, you need to know about the protection relays. You need to know about the different techniques for transferring the technical information and data from one point to another. You need to know a number of things about the Scada system, about the PLCs, and things like this. Okay? So in order for me to tell you about this IEC 61850, I need to tell you some background and back of the stage information, so you are prepared to get the concept of that standard. So therefore, as I said, the idea is to get remote access to substation devices, right? So you have got transformers, for example, you have got power transformers, you have got reactors, you have got cap banks, for example, you have got meters, you have got a lot of other things. For all these, you have got the information such as current, such as load current, fault current, over voltage, under voltage, under frequency, over frequency, things like these. So the idea is to, first of all, have the remote access to all these things, and second of all, being able to analyze the information. But there are some differences between this 61850 technique and the more traditional ones that I'm going to express. So basically, I'm going to tell you in terms of this remote access and remote control, telling you about the Scada system, and in particular about its remote terminal unit, or RTU. I'm going to tell you about the programmable logic controller, or PLC, and I'm going to tell you about the intelligent electronic devices, or IEDs for short, which covers a wide range of protection relays, control gears, monitoring devices, metering devices, comms, and SCADA. So these are the things that we need to learn. So first things first. We are going to talk about remote access, isn't it? Remote access by who? Remote access by the operator. Remote access by, I don't know, the decision makers. So therefore, there must be an interface layer between the machine and the human, because the information that is absorbed and collected and gained by some devices like sensors, for example, CTs, VTs, and the like, cannot be directly understood by the human. Likewise, the instructions and commands that are issued and released by human are not understood by the machine. So there must be an interpreter in between. There must be an interface layer between. That is what we call the HMI. It can be in the form of push buttons. It can be in the form of personal computers, the keyboard, for example, the mouse, many different things, right? Whatever that can come in between and act like an interface layer. Then we have got the concept of IEDs. So previously, engineers and technicians used to refer to protection devices as something like relays. But these days, these kind of things are mini computers. They are multifunction. They are not only protection, but are also capable of being connected to control gears, intelligent control gears, monitoring devices, metering devices, other Scada RTUs, PLCs or something. They are able to exchange the information, communicate at very, very advanced levels. For all this, we prefer to call them IEDs rather than just a simple word for one function. So from now on, every time I say IED, it can be anything. I may be referring to a smart meter. I may be referring to a digital protection relay. I may be referring to a very, very advanced and sophisticated control gear, such as the Scada RTU or PLC or something. They are all examples of this IED. But the beauty of that is that these days, all these IEDs can talk to each other. They can communicate the information. So in other words, you have got a big cube. Inside this cube, you have got a lot of information, a lot of signals, right? A lot of data. But what happens is that this cube, this box, has got a number of gateways. In other words, you can get access to this information from many different points. From the location of the relay, from the location of the meter, from the location of the control gear, from the location of the Scada system, from the location of the PLC, from the location of the Scada master station, from many different points. That is the concept, first of all, of the 21st century substation automation. You need to be able to get access to this information and control the system from any point, from many different gateways. Therefore, you need to talk to the devices, isn't it? There must be a language between. This language should be well understood by all those IEDs. A relay should be able to talk to PLC. The PLC should be able to talk to RTU. The RTU should be able to talk to a smart meter. So all these things should be able to well communicate with no problem. The name of that language is what we call the protocol. So we need to have a comms protocol in between, which can be in many different forms. It can be DMP3, it can be Modbus, it can be Profibus, it can be RS-232, and it can be 61850. So that language, that comms protocol is important. But the beauty of this 61850 is it is not just the language, it is not just the protocol, but it is also related to system configuration. Right? So that is the difference. Well, obviously, there needs to be, I don't know, a port, a jack, I don't know, something, so you can connect your data cable to that IED. This is what we call the serial port. By means of optical fiber cables, for example, you just connect your system via that serial port to that IED, and by means of communication systems, you should be able then to transfer that information to other places. So that is the idea. This is what we are going to achieve. So one of those gateways, as I said, is the Scada system. This is Scada system, which stands for Supervisory Control and Data Acquisition, has got a number of roles. First of all, it says supervisory control. Supervisory control over what? Over the status of the power system data. Status, yeah. For example, the status of frequency. I want it to be 50 Hertz, not 51, not 41, just 50 Hertz. So I'm just concerned about all the other frequency. The system is 132 kV. I just want it to be fixed at that. So the areas of concern are over voltage and under voltage. So that is what I mean to say by the status of the power system collected data. So that is the meaning of supervisory. Right? And what is data acquisition? Well, there must be some means of collecting the information from the field devices, like transducers, like sensors, and that is the stage when we call it as data acquisition. All right? So that's a combination of that. So basically what happens is that it needs to have a mastermind. This is what we call the master, let's say Scada master station, and a follower, or a device that should be able to do the initial analysis on the collected data. And this is what we call the terminal unit, or RTU. So a number of RTUs can be connected to one single master station, or there could be some sub-master stations connected each to a number of RTUs, and then all these sub-master stations be connected to a master station. All right? So this is how it works in here. So as I said, the remote terminal unit is the point where you receive the information from the field devices, such as the CTs, such as the VTs, such as the sensors, the transducers that control pressure, control height of a liquid, control frequency, control vibration, control temperature of what? Of transformer winding, for example, things like these. All right? And then analyze the information, save the information in some kind of memory cards, digitize the information from analog to digital, and then transfer and communicate and exchange that information with other IEDs. All right? So that's how it works. Therefore, what is RTU? Scada RTU is a device that is intelligent enough to control multiple processes. So it is not just connected to one CT or one VT or one sensor. It should be capable of doing data logging and alarm handling if required. Should be expandable. I should be able to add to the number of memory cards, or I don't know, things like this. Processors, microprocessors. It asks the field devices for information. Yep. So that is the input. It can control other IEDs. Yes, if I like. I can control from one RTU. I can make a connection to other RTUs, other relays, other PLCs. It depends who's the boss, who's the follower. I can change the roles. One day this RTU is the boss, another day it is the follower. All I'm saying is that I can define a master-slave relation in between. Therefore, the RTU is the first point of contact to do the alarm acquisition and processing, measuring values, fail-safe command, communication with the Scada master station, and one of the main roles is to synchronize all these processes in terms of time. So that when we say it's going to be done in 1 minute, in 1 second, or whatever, all those IEDs that have been connected together have got the same understanding about that time. So basically, the main components of this RTU are the CPU, of course, central processing unit, the power supply. At the end of the day, that's an electronic device. Some input-output modules, IOs, could be digital and could be analog. It should have a software, of course. That's a computer, at the end of the day. It should have some means of communication like those serial ports. It's got a frame, and of course it's got a chassis. So that's the building block of RTU. Now, you are going to connect your SCADA master station to these RTU or RTUs. As a result of that, you need to have a communication link. It could be many different things. One of the ways, for example, it can be by means of modem and telephone line, dial-up connection. It can be radio. It can be a LAN system such as the Ethernet. So there are many different ways you can connect this master station, SCADA master station, to RTUs. Basically what happens is that these RTUs receive the information, they store the information, they analyze the information, they process the information, and if required, and if it is asked by the SCADA master station, they will dispatch the information towards the SCADA master station, or they should be able also to send it to other RTUs, share the information with other PLCs that are somehow connected to the same master station. Right? So that is the circulation of the information. Pretty much similar to what we say about a substation. We say bus bar. That bus bar is a power bus, is that right? In here we have got a data bus. Not just one, more than one. So the information goes from one data bus to another data bus by means of these IEDs. Okay? So you can get access to the information from many different gates. As I said, that is the idea, but you need to make sure the language is well understood by everyone, that protocol. You have already provided enough security for safeguarding the information on these buses so that no unauthorized access is permitted. If required, you need to encode and then decode the information, and this is what we call as encryption. Okay, so there are different considerations in between. So as I said, depending on what's available to you, whether telephone lines have already been established between the 2 points, or you have got a radio communication, you have got a mast, for example, you have got modems available, if there are any hills or mountains in between, if you have got satellite available, or if you have got fiber cables available or something, depending on the distance between the 2 points, your decision for communicating between all these RTUs could be different. Well, another means of collecting and analyzing the information, especially in industrial sites and also in our zone substations, is what we call the PLC, or Programmable Logic Controller. So first of all, it can be programmed. It's a controller and it has got a logic. It means that you can program that to a logic so that, okay, first of all you do this, then second and third and fourth, especially in manufacturing companies, like car manufacturing companies where robots are working, but those robots are controlled and commanded by means of a number of PLCs. The same concept can be used in a substation, right? For controlling the switches, for example, for controlling system parameters or something. So basically the concept is pretty much similar to RTUs, but RTUs are more used in substations. PLCs have got very wide application. They are in substations, and also they are in, they can be found in the industry. So, as I said, it's got a language, isn't it? The name of that language is the ladder logic. Pretty much similar to any device that you have got these days. It's got a language. Even a relay has got a language. You need to learn the language in order for you to be able to program that device. So I'm not going to go into the very details of the PLC, let's say, programming language or something. But all I'm saying is that you should be trained in that. If you are going to work with PLCs, if you want to change the settings of the PLCs, if you want to change the functions of the PLCs, okay, do this, don't do this or something, you need to be able to be trained in that ladder logic controller language. So again, it has got a number of memory cards. It has got volatile and non-volatile memory. It has got a controller. It's got a microprocessor. And it should be able to understand that language or protocol. So, in other words, it's a microcontroller. It can be connected to the relays. It can be connected to the meters. It can be connected to other controllers to do many different functions. So obviously, it provides you with a lot of flexibility. As long as that logic, that control logic is well understood by others, it should bring about compatibility. It should bring about the ease of adding or exchanging inputs and outputs, changing the configurations of them. Directly or indirectly, it will help increasing the overall reliability of the system. Of course, it can facilitate for better troubleshooting of the system. So all are advantages of this PLC. So basically, you can see the block diagram, very similar to that RTU. It's got a power supply, of course. It's an electronic device. It's got memory cards. It's got microprocessor, central processing unit, CPU. It has got a number of inputs and outputs. And it can be connected to many different things, to switches, relays, valves. It depends. Where are you going to use this PLC? Now, in a very similar manner, you can connect the Scada system rather than connecting to RTUs. You can connect to PLC. Again, you need to have a communication link, like field bus. The PLC, similar to RTUs, are connected to a number of sensors, basically. But as I said, these PLCs can be connected to other PLCs, can be connected to other RTUs, can be connected to other master stations or sub-master stations. And the idea is to remote control, to do all those settings and changes and configurations and programming and everything remotely. Why? Well, because we are going to save a lot in terms of the labor, human force that is required. It is not like 20th century or something. You do not need to have a lot of people in your power stations or substations. That is the idea. These days, if you go to substations, there's no one there. There is no need to hire someone to be there. Everything is fully automated, remote controlled. Well, as long as there is no fire, there is no accident, there is no short circuit, there is no arc flash, there is no nothing, why should anyone go to those places? That's the idea. So what are the advantages? The computer can record and store a very large amount of data in that PLC. All right. The data can be displayed in any way the user requires, like a printed copy, for example, like the saved information as a file, for example, like in a logbook or log recorder or event recorder or something, anything that you want. Thousands of sensors over a wide area can be connected to the system, so it will provide you with filtering, it will provide you with data identification. The operator can incorporate real data simulations into the system. But who's going to synchronize this information? The PLC. Many types of data can be collected from the RTUs. As I said, these PLCs should be able to communicate the information with other IEDs. The data can be viewed from anywhere, not just on-site, and that is the main concept. Are there any disadvantages? Of course. The system is now more complicated. Compared to what? Compared to the old system, traditional. Previously, well, what was your problem? Wiring. What is the need for this IEC 61850 or other things? Wiring. I'm just going to get rid of all those wires and wires and wires. I just want everything to be wireless as much as I can. No termination. Marshalling boxes, termination boards. I'm just going to get rid of as much, not totally, to a large extent. Get rid of that. So who's going to make the decision? Who's going to make the connections? The microcontroller. Okay, microcontroller, yeah. By means of what? By means of 61850. This is what I want to achieve. So that 61850 should be a solution maker in terms of many different things. In terms of the communication protocol, in terms of terminations, in terms of wirings, in terms of the control logic, in terms of the interlocking, in terms of many different things. Everything should be included in that 61850. You have got an open, you have got a very big idea in your mind. So that system should be very comprehensive. You are going to connect thousands of sensors. You are going to connect other systems to that. Something like this. See, you have got RTUs, you have got marshalling racks, you have got a lot of relays, transducers, you have got switchgear, you have got, I don't know, this comms protocol like Profibus or something. You have got a lot of things, Ethernet. The idea is to simplify this. This is what we are going to achieve for 61850. Other than that, the system is already available. Some of you have already raised the question, why is that so? What are the applications? What are the limitations, problems? Well, I tell you now. As long as you have got a greenfield project, not a problem. You can establish everything from the outset. That's at your control. If it is a brownfield project, we have got problem. Retrofit. Well, already you have got a lot of panels, mate. You have got a lot of wires. You have got a lot of terminations. You have got a lot of logic, interlock. It will be an absolutely complicated job. I'm not saying impossible, but very difficult to change all this from the traditional system to the 61850. When rather than all those wires and wires and wires, microcontrollers come in between, electronic switches come in between, digital switches come in between, rather than those physical auxiliary switches or things like this. Well, you have to be able to adapt what is required by 61850 by what is available in your site. That's the problem. Not everyone can do it. You should have a perfect understanding about the existing system first, and then understand the requirements of the 61850, and then as an engineer think for yourself. Can you match? How can you retrofit? How can you replace? If I just get rid of all this panel with all these wires and switches and auxiliary contacts and whatever, then what? What is the thing that can fit in between? So I need to understand what are the inputs first, what are the outputs second, and it's not just like for like something, another box I put in between. No, because fortunately or unfortunately, this 61850 is not just a solution maker for wiring, but also it is changing the configuration. So that can add to the complexity. So one more time. As long as the system is greenfield, nothing's been established before, perfect. You can establish that, no hassle, no panic. If it is brownfield, well, I'm not saying impossible, I'm saying more difficult to do it. So the first thing is that you need to understand those IEDs. I've already talked about PLC. I've already talked about RTU. What about relays? Well, modern relays we are talking about, right? Obviously, I'm not talking about those very old induction type, disk type, electromechanic type relays. No, I'm not talking about that. I'm talking about modern numerical digital relays. They are IEDs. They are the ones that can be connected to SCADA RTUs, to PLC, to comms, to smart meters. This is the thing I'm talking about. Well, in terms of function, they may have a number of different functions like overcurrent, earth fault, differential, voltage relay, frequency relay, distance relay, many different things. You know these concepts. They can be used for the protection of a feeder, for the protection of a machine, like a generator, like a motor. They can be used for the protection of a transformer, for the protection of a transmission line, for a distribution feeder, many different functions. It can be an overload relay. It can be an overcurrent relay. It may have to do with three-phase faults or single-phase fault. Many different ideas. But all I'm saying is that these kind of IEDs are using digitized information. As soon as you understand this, you should be able to put that in practice and then control everything by 61850. That's a very simple example. You have got a motor that is protected by relay number 1 to be backed up by relay number 2. So there's a fault. If the fault is at the location of relay between relay 1 and 2 and the source is on top just, while relay number 1 is not involved, relay number 2 just operates. What about if you have got a small power at the location connected to relay 1? In that case, you have got feed to the fault point from 2 points. That's one of the things. Another thing is that motor, you understand, okay, you would say, well, that's a load. Yes, that's a load, but what about if it's a synchronous motor? So what? What I'm saying is that as long as you have got normal operation, that motor is a load. Upon occurrence of a fault, that motor suddenly changes into a generator for a few moments and will have a fault contribution to the fault point. All these things are very complicated. You need to have a very good controller to understand the direction of the currents, to understand the roles of the relay, who is main, who is backup, and put that in practice. Program, analyze, do the wirings as less as possible, and off you go. And then this story is continued by checking the coordination between the relays. Well, I've got the curve of the motor. All right. So this motor, first of all, is going to be protected by main protection, which is relay number 1. If relay number 1 fails to operate, relay number 2 will come in and take over. So obviously, The curve of relay number 1 should be above the curve of the motor. Otherwise, for motor operation, even under normal load, the relay will trip. This is not what we want. Okay? And there must be a gap between the operating time of the relay number 1 and relay number 2, as you can see in here. So that is the concept. But if, however, these two curves of the relays intersect with each other, in that case you have got problem. In that case, the backup protection may operate first for some particular currents. So as you can see in here, in low currents, for example, as you move to the left, it is quite possible that relay number 1 operates first and then relay number 2. But as the current increases, relay number 2 operates first and then relay number 1. Okay? So it depends on the application. Sometimes, again, by means of that communication, you are, for example, applying intertripping techniques, so that as soon as one relay operates, a signal is sent to other places, say, hey mate, I would like you to operate as well at the same time, or quite the contrary, the relay may ask the other relay, for example, at the other end, hey, this is not the fault, you should operate, I'm just going to block you because it is out of your reach. It is not your responsibility to trip for that. So that is a blocking signal. So who's going to do all these things? That IED. That IED has got enough intelligence and power to put all these things into practice. You have got many different manufacturers like Siemens, like ABB, you have got Alstom, Arriva, I don't know, things like this, Micron. You have got GE, you have got GEC, many different manufacturers. They all, SEL, for example, they all produce these things that are responsible for protection, control, monitoring, metering, communication. But the beauty is that they are all compacted in one place. In other words, these IEDs are multifunctional. These days, a protection relay is also a meter. It is also a means of communication. It is also a monitoring device. It is also a control gear, all in one place. Right? So that is important. The important thing is that this device should be compatible. These days it is not acceptable that, hey, my products are all American made. So they cannot communicate with German-made devices. No. It's not like that. It's not like that. It should be compatible. Whatever language I speak, you should be able to understand. Whatever language you speak, I should be able to understand. It really doesn't matter. A Micron relay sends information to, I don't know, GEC relay. Not a problem. They should be able to exchange. They should be able to trip. They should be able to store. It's more like a selector switch. I can talk in many different languages. I can talk C1850. I can talk DMP3. I can talk RS485. I can talk field bus, Modbus, many different things. Okay? So these are the things to understand. So if that IED that you have got is mainly a protection device, well, it can provide you with directional or non-directional protection against what? Against three-phase face-to-face faults, for which its overcurrent element will work, or single face-to-earth fault, for which its earth fault element will operate. It can also be equipped with over-under voltage device, over-under frequency device, overload device, for example, in terms of transformer inrush or motor restart up. It could be an example of a protection IED. I can define a lot more functions. That was just an example. Or that IED may be a control device, a microcontroller. In that case, well, the role is completely different. It should be able to be connected to a number of auxiliary switches, main switches, data switches. It has to do with interlocking. It has to do with connection to the HMIs. It has to control, right? What do you mean by control? One of the control thing is sequencing. It's more like a number of people are standing in a queue. There must be someone to organize these queues so that people are not jumping in, right? It should be ordered, not disordered. There must be a sequence. First of all, do this, and then if fails to operate, do this, and then. This is what we call the control. Well, sometimes it is just monitoring. That's another story. Monitoring what? Monitoring, for example, if the trip circuit of the circuit breaker is healthy. It doesn't have any loose connection. It doesn't have any disconnection. It doesn't have any failure of the power supply. So what is the role? The role is trip circuit supervision. The role is TCS. Okay, so that relay, for example, that is a TCS relay, yes, or TCS element, yes. Sometimes you are checking if you have got an SF6 switchgear, SF6 circuit breaker, for example, the level, the density of that SF6, because if it drops down, the SF6 will lose its physical and chemical properties. Sometimes you are monitoring events, how many shutdowns, how many trips, how many alarms. You're going to hand over to another operator. You're going to hand over to another technician. So what has happened so far? So these are the things, sometimes monitoring temperature, pressure, frequency, vibration, harmonics. A lot of things to be monitored. Sometimes the role of that IED is metering. Like what? Like a smart meters. They are exchanging a lot of information with the utility company, like your active power, reactive power, frequency, voltage, current, power factor, energy, harmonics, a lot of things like that. And the utility company is also commanding the device based on the information they are receiving from your residential property. So again, can I connect this to another IED? Yes, you can. Can I read the information from other RTUs? Yes, you can. From other PLCs? Yes, you can. Very good. So that's all good news. Is that right? As long as what? As long as you have got good control over the traffic of the data. So the things are not going to get confused. As long as those queues, those sequences, they are ordered and not disordered, everything's fine. Everything is within your control. Other than that, if things go outside your control, that would be a chaos. And you may face a lot of unwanted shutdowns and trips that you don't like, or miscommunication between IEDs, misunderstanding of the commands, and you, guess what would happen after that. So all I'm saying is that this functionality is important. As you can see in here, we have got a lot of different layers. Look to the right, we have got RS485, not a problem. We have got Ethernet LAN, not a problem. So look at the very bottom. You have got 3 relays, for example. One of them is URL90, which is a line protection device. Another one is URF30, which is a feeder protection device. Another one is a URT60, which is a transformer protection device. Not a problem. I can connect all of these things together and I use an Ethernet LAN or local network, access network, and then exchange this information with a lot of other devices. Look to the top. I've got other protection control devices in there. They have got elements 50, for example, which is the instantaneous overcurrent. They have got elements 87, which is the differential protection. But whatever it is, they have got a logic. I can use devices like flex logic just to bring everything under control. As you can see, I've got analog and digital inputs and outputs, virtual outputs. I've got physical outputs. Not a problem. As long as I can control all these things, I understand which one is actual, which one is physical, which one is analog, which one is digital. So what's the point? The point is I need to have appropriate switch. Do I need to have digital switch? Ethernet switch? Do I need to have a hub? What? What is the thing or things that are required to achieve this functionality? So if you have got to do with protection IEDs, well, have a look at the difference between electromechanical and digital. Well, these digital ones have brought about a lot of things in terms of reliability, stability, sensitivity, speed of operation. That's perfect. Multifunction, for example, versatile, very sensitive, for example, data communication, control functions, even metering. These days you don't need to worry about CT burden, for example, or interposing CTs. All is calculated by this IED. Cost? Well, it depends how complicated your system is. How many backup, local, remote, whatever. So it all depends on that. So all I'm saying is that yes, new technology, IEC 61850, DMP3, they are very good, but sometimes depending on the complexity of the system, that may cost you a lot of money. But of course, when you've got a complicated system like this, obviously, if you have got controllers, for example, you are using modern relays like this Cyprotec generation of protection relays that belong to Siemens. All right. So I have got a number of these relays. I have got them connected to a data bus by means of many different things. For example, some of them by means of Profibus, some of them by means of IEC 6870, some of them by means of IEC 60 other generations. So all that matters is that there must be a controller in between so that all these devices can talk to each other. The configurations, as it says in here. So what do you mean by configuration? Well, what do I mean by configuration? Well, the idea is to send the information from one place to another, right? Well, I can do it in many different ways. What do you mean? Well, I can sort out this information into many different packs of info, packs of data. First, this can be a change in the configuration. Second, I can send this information and receive this information at many different speeds. This is another change in the configuration. I can encode the information. I can put a token ring in that so that devices actually receive this information in turn. Well, I can do a lot of changes in the configuration. I can double the data buses. I can triple the data buses. I can connect the data buses together. So I'm just adding and adding to the number of gates. I am adding to the volume and the amount of data to be transferred in each second or microsecond or millisecond. Can I do any other changes in the configuration? Yes. I can send some pilot signals for security, just for the other party to understand whether this signal they have received is a genuine one or not. Has it been issued by me or not? Well, I can do a lot of changes in the configuration, and your device, your IED, should be able to do that. As long as you have been well trained, you understand the language, you understand the concept, you understand the protocol. Now that I've said that, well, so the idea is to send the information from one place to another. So you have got a network, so I'm not, well, first of all, you have got a power network, right? Power stations, transmission, distribution, substation, whatever. So that is the power network. In order to automate that power network, you need to have a data network. That data network has got a particular configuration or topology, as we say. Again, regardless of the amount of data that you are sending, regardless of how you have grouped them together, regardless of at what speed you are going to send this information, there are other considerations as well. Like what? Like, okay, like whether you are going to make it point-to-point or point-to-multipoint. What is the difference? The difference, reliability. The difference, cost. The difference, redundancy. That's it. Point-to-point, point-to-multipoint, maybe good, maybe bad. Okay, so they have got their own advantages and disadvantages. If you lose, for example, one of the connections, so what's going to happen? Is it point-to-point, for example? Well, if you just lose the connection between point A to point B, then what? Okay, so make it point-to-multipoint. Point-to-multipoint? Yeah, okay, not a problem. What about if you lose that point, like point A? Okay, in that case, nothing will go to multipoint. Okay, so we have got a number of risks. So there are other ways you can make changes in the topologies, like, for example, the bus topology, star topology, ring topology. So what is that? This is bus. Pretty much similar to a bus bar, power bus bar. But this is not a power bus bar. This is a data bus. You've got a server and you have got a number of users. All these are sharing the information. Pretty much similar to what is happening in your office. You log in every day. I'm your colleague. I am logging as well. I can see exactly the system as you can see. But maybe my authorization is different from yours. So there are some documents I can see, you can't see. There are some documents you can see, I can't see. But at the end of the day, we can see each other. I can send you an email. I can record my voice on your voicemail. So where does it come from? From that bus in between. So we are sharing the information. So advantages, uses relatively less cabling compared to other topologies. So that's the idea. There's why they just connect all the computers in the office to the same server, to the same network, is this. Saving a lot of cabling work. Easy to add or remove nodes. Yes, I am a new employee. Your IT comes in and add me as a new user. Easy. Or I have already resigned. Well, my email account will expire and things like that. So my node will disappear. It has got a simple and flexible architecture as well. So it can dispatch the information to many different places. It is inexpensive. Cable and connectors Are there any disadvantages? Well, we have got security problem. As I said, every node can hear every message. So you need to have firewall. You need to have encryption. You need to have authorization. You need to have security to be enabled. Who does it? IT. And now that everything's been connected, if there is a fault, you may have noticed that sometimes you come to the office and say, hey, this whole system shut down. It is not a matter of 5 minutes or 2 minutes. It's shut down 2 hours. And you and your colleagues are just sitting at the office doing nothing. Because of what? Because those guys cannot find the fault. Let's say, finding could be a pain. What about a star topology? Star topology, in that case, you need to have a center point, like a hub. So all these machines are talking to the hub, and through the hub, they can talk to each other. Is it good? Wow, it's very good. That's face-to-face conversation. But what about if I just lose that hub? Uh-oh, everything's gone. Yep, remember that. Remember that, again, you are saving a lot in terms of cabling, wiring, or something, but remember that if you lose that hub, what would happen to the whole system? So what about the advantages? Well, troubleshooting is much better. Easy, again, to add or remove nodes, not a problem. You have got a central hub that allows monitoring for management purposes. Management. So this hub here is responsible for data management. Any disadvantages? Yes, as I said, if that hub fails, then what? The whole network fails. It really doesn't matter whether you are using IEC 61850 or anything. If you lose your hub, finish. Well, I would like to have full reliability. Very good. Ring topology. It's very similar to what we do in power networks. So any machine can be supplied from 2 points, not from one. But if one of those nodes is gone, in that case you have got a disruption in that ring. It is not a power ring, it is data ring. So the transfer of information can be disrupted. So advantages, physical ring has minimal cable requirements. So again, my dear friends, we are aiming to reduce cabling terminations as much as possible. We are just trying to make the system configuration as cheap as possible. The migration from RS-232 to 485, from Modbus to Feedbus, from all these things to DMP3, from DMP3 to 61850 has got an intention. We are just going to simplify the system. Why? Because we are going to make it cheaper. That is the idea. We are going to make it multifunction. We are just going to make it versatile. We are just going to make it easier to access remotely from many different points. That is the idea. So that's why we just make it ring topology. But as I said, you have got a token ring. So this token is just going from hand to hand, from station to station, from node to node. Is that my turn? Yes, send information. Oh, that token's gone. Okay, just wait, it will get back. So in your next receive, just send the information or receive the information. Is it good? Well, it's more like I am the organizer here. I have to put people into queues. That's how it is. So that's advantages. Disadvantage, well, as I said, if a node fails, the whole ring fails. Adding and removing nodes, this time it is not as easy. Previously, for a star bus topology, we said what? We said adding and removing nodes is easy. Yeah, but here you have got a ring, If you add or remove, it requires you to disrupt, to shut down first. And that is what is happening in here. All right. So this is the end of presentation number 1 and pre-recording number 1, and I will continue in pre-recording number 2. Thank you, and I'll have you in pre-recording number 2. Thank you and goodbye.